have to guess and check to find that t in problem like 6c, there really isn't a good way for you to solve for an exponent. Well, there is, we just haven't learned it yet, right? The inverse of an exponential is a logarithm. So what we're going to do is just talk about inverses today. And inverses are used in many different ways, right? Inverse is a word that's used in a ton of different ways. We use the word additive inverse. The additive inverse of 3 is, yeah, -3, because they will add up to equal to 0, right? Not necessarily, but some of the terminology shows up on like essay quizzes, so it is important. Multiplicative inverses. The multiplicative inverse of 5 is, that's a different property that I can't think of the name of. So multiplicative inverse is sort of like the reciprocal. So it's 1/5. The goal is to multiply to be 1. So if I were to multiply 5 times 1/5, that would get me to 1, right? So there's different ways to use the term inverse. And personally, I like the function version of an inverse. So if you're going to use the function version of an inverse, and this is important, to graph the inverse of a function, you can reflect each point across the line y is equal to x. And this is equivalent to switching the x and y values. This might show up somewhere on an essay quiz, this idea of an inverse. So once again, to find the inverse of a function on a graph, you can just reflect the points over that line y equals x. Or if you're looking at a table of values, you can just switch the x and y and then graph them again, right? Personally, I think switching the x and the y and writing new coordinates down is way easier than trying to find like the reflection, those perpendiculars across the line, y equals x and blah, blah, blah. So I'll show you both ways with this graph, but we will probably stick with the switching x and y, and then I'll just show you a sketch of what the reflection looks like, right? So anyway, we're going to be graphing the relation and connecting the points. So this is the original relation. So if you have two colors, you might want to use them today. If you don't, not a big deal. So this is our original function. So we have 1, 0. Oops. No, that's right, isn't it? 1, 0. 3, 1, 4, 2, 5, 3, and 6, 5. So yes, you will need a graph in front of you. This is my original relation here in the blue. And remember, there's two different ways to find the inverse of a function. So you can either reflect or switch across or switch the x and y. So for the inverse, we're going to switch x and y. So in this case, our x's are now going to be 0, 1, 2, 3, and 5. And then our y values are now going to be 1, 3, 4, 5, and 6. Do you see how I just switched the top with the bottom? And let's look at what this looks like on the graph, right? So if we were to start plotting these new coordinates, 0, 1, 1, 3, 2, 4, 3, 5, and then 5, 6, those two pieces look oddly familiar, right? Kind of nice. Those sketches do look eerily similar, And then if we were to sketch this line of reflection that we just talked about, that line y equals x, if we were to sketch that line, that means it's a line with a y-intercept of 0 and a slope of 1. This is our line of reflection that y equals x. Do you see how every single point is the same distance from this line? The tricky part about doing the reflections over the line y equals x is it's not just like up and down. So you have to like turn your paper to the side and go kitty corner to kitty corner. But if you're a visual person and like measuring distances corner to corner, go for it, right? So once again, I like to switch my coordinates around. You can reflect across the graph as well. But when the relation is also a function, you can write the inverse of a function as f negative 1 of x. This is not a reciprocal or a negative exponent. So that negative 1 is really not f to the negative first power of x. This is literally read the inverse of f of x. It's just a weird notation to indicate the inverse, okay? So once again, the inverse of a function, f of x, is written like this. It does not mean a negative exponent. So if we have functions that undo each other, those are called inverses, right? So the inverse, functions that undo each other, well, addition undoes subtraction, right? Multiplication and division. How about like x squared? What's the opposite of squaring? Square roots. So for exponentials, we're going to have logarithms, right? So these are all inverse operations of each other. In order to find the inverse of a function, this will also show up on an essay quiz. The two-step. I'm sorry. That's a throwback from my middle school time. Most of you probably have no idea what song I'm referring to. Anyway, so the first thing you need to do to find the inverse is to switch your x and y around. So just like what we did with those tables up here, right? We're going to switch the x and y, and then once we've done that, we're going to solve for y. Okay. Another big thing that might show up on an essay quiz, can you tell vocab with inverses is really important? Hopefully, cough, cough. If we're talking about inverses and we're referring to something like a t-chart or coordinates, we just talked about this. For inverses, the x's and the y's are switched, right? If your x's and your y's are switched, doesn't that also mean your domain and range are switched? On a graph, right? And then both of these things also imply that your inverse is reflected over the line y equals x on a graph, right? So if we're going to talk about, I ever say, what do we know about a function and its inverse? You can say x's and y's are switched, domain and range is switched, and it's reflected, all your points are reflected across that line y equals x, right? If I say, how do I actually find an inverse of a function, that's when you would give me the two-step. So if I'm looking at using inverse operations to write the inverse here, so step one, first of all, I'm going to use x and y. step one is to switch where my x and my y are, right? Remember, f of x is the same thing as a y, really. It's just function notation for y. So what am I going to do? I'm going to switch where my x and my y are. And then step two, I got to solve for y. So using inverse operations, I'm probably going to divide that 3 out first. Right? I need to move that 3 to the other side to get x over 3 equals y minus 7. In order to get y by itself, I need to add 7 to both sides. So I'm going to get y equals x divided by 3, and then I added 7, right? So this is my equation, but I need this in function notation. And remember, to indicate that this is the inverse function, I need that f, the -1, and then the x, and then I'm going to write my new expression. So your answer, your final answer, you just got to shove it back in function notation again for inverses. That sort of makes sense? Okay, last thing we're going to do is, it says graph our original function, so I'm going to use 2 colors again. So I have my original function I'll stick with in blue. Lucky for us, this is just a linear equation, right? So we can plot our y-intercept of 2. Notice how your graph is counting by 2's. So if I start at 2 and I go up 2 over 3, up 2 over 3, up 2 over 3. This is my original function, f of x. I do need to find its inverse. I need to find the inverse of y equals 2/3 x plus 2. So in order to do that, step 1, switch your x and y, right? And then step 2, I got to solve this guy. I'm going to subtract the 2 to the other side to get x minus 2 equals 2/3 y. And then my favorite thing, when I divide by fractions, I need to do keep, change, flip, right? Kentucky chicken fries. Sorry, that's what my 7th graders called it last year. I don't know, it kind of stuck. So we're going to keep the x minus 2. We're going to change the division to multiplication, and we're going to flip that fraction. And then we have to distribute, right? So I'm going to get y is equal to 3 halves x. 3 times -2 is -6 over 2 is -3. But I still have one little tiny step, right? This is not in function notation, so to write my inverse function, I need to use that function notation. Right? So if I were to graph this inverse function, you're going to see a y-intercept of -3, and I'm going up 3 over 2. Up 3 over 2. Up 3 over 2. And we're going to draw a line. So a good thing to check is either check your coordinates and see if your x and y are switched, right? Here I have 2, 0 and 0, 2, right? This one I have 4, 3, and then I have 3, 4. So it looks like our x and y are switched. Or You can always sketch that line of reflection and see, does this look